Hello, AP Statistics students, and welcome to your first video of the year. You've come to the right place, but only after you have read the textbook. The way this flipped classroom setup works is that you first go and read the textbook and study it well and try to go through the notes yourself as well and just do your best to understand the whole sections. You have to read the textbook first before you come to here. The videos are not meant to be an all-inclusive place to go to learn everything. You have to read the textbook first. Then you come to here and your teacher, either me or whoever else is teaching with me, Miss Ortwine or whatever, will try to enhance what you've learned a little bit from the book. We'll try to point out the main features and also try to make connections or point out things that maybe you didn't see when you read the textbook, things that we think are important or connections that you can make. So this is only after you've read the textbook, okay? So I'm going to say that 1,000 times, but read the textbook. It's super, super important that you do so. If you're not doing so, then you are not doing what you're supposed to be doing for this class. Okay, so go read the textbook, come back, and then start here and watch the rest of this video. Okay, so you've read the textbook and you see that the first couple chapters, this video covers the first couple chapters in your Pearson BVD book. The first couple chapters are all about just displaying data, how to kind of organize and display data. So I don't want to get through too much here. And also you kind of are getting like wrapping your mind around what statistics going to look like, what's it about, and that kind of thing. And we'll talk more about this in class as well. The big, what you see on this screen right here on this slide is trying to get you to like there's kind of three things that maybe you can think about as we're going through statistics. This one, are apples cheap in Japan cheaper than apples in the United States? Well, the whole thing, like you could probably figure this out. You'd say, well, let me go find some apples in Japan. That's going to be in yen, and then I got to go to the United States and get some prices of apples there, and that's going to be in dollars. I'm going to have to do a conversion somehow, and then I'm going to have to compare them. And of course, where did we get the numbers for the prices of the apples? Did we go to the really nice place in Japan, or did we just go to a grocery store? And same thing in the United States. So it seems like a simple problem, but that's the thing about statistics, is that there's all kinds of ins and outs and little corners that you have to worry about and think about to really get a good picture. And you're trying to paint the best picture you can for whoever you're reporting to. You're trying to describe something. I mean, this, like I said, the Apple situation sounds really simple, but it could be difficult if to get it just right, so that you're giving the best representation of the truth that you can. This whole class is about what's the truth, and the weird part is you're never going to know the truth, almost never, unless you do a census or something. But you're almost never going to know the truth. You're trying to paint a picture to find out what the truth is as best you can and display that to the audience or to your reader. The second one here is the number 99 good. This is all about context. Nothing makes any sense in this class unless you put context on it, unless you describe it in context. 99 could be good if you're taking a test, right? 99 out of 100 on a test, that's good. But if it's a bowling score, a perfect score in bowling is 300. So 99 wouldn't be very good. Context, context, context. The next piece down here, it's trying to point out to you that in statistics, people try to use stats in their own, or to kind of support their own agenda. And it happens all the time in the media and all over the world. It's one of the things about stats that, just going through this class, when you leave, you're going to be more aware of how people are trying to trick you with statistics. It's not that they're outright lying. It's just how they display it or how they word something can really change or influence people. And sometimes that's really wrong, and but they do it anyway, right? Because they want to get their way. So you can see here, like it says, which is more frightening? One out of every 100,000 U.S. citizens have been diagnosed with the bird flu. Or if you read 3,000 cases of the bird flu have been diagnosed in the United States. Now, this could be used for, we got the COVID thing going on. This could be used to kind of like try to skew people one way or the other about vaccinations, or who knows what, right? Trying to get people to be scared or not so scared. So these are actually the same. Like this is the exact same number and the exact same, it comes from the exact same data. It's just worded in a different way, so it feels a little different, and it's used to influence people. So that's a big thing about statistics is we don't want to, like, for us, we're trying to just tell the truth. We're trying to analyze things, but you're going to see that in the end, you're going to be more savvy about how you use stats to influence people, or seeing how people try to influence you and other people using stats. Okay, two big categories. We got quantitative and categorical. And like I said earlier, we're trying to display data. The first two chapters in the book are just about how to kind of collect it, not really collect, but how to display data once you get it. So quantitative is numerical. A lot of times you'll see things. I put some numbers in my TI Inspire here for high jump. You'll see we're going to use a spreadsheet a lot. So I put in a spreadsheet. These are just like meters for the high jump, let's say high jump A and high jump B. And I just put in a whole bunch of numbers, 1.5 meters, 1.4 meters, 1.6 meters. But to display that, we have different choices. We have a dot plot like this. I can change the plot type here. We have a histogram, right? And I can compare the histograms then. Normally histograms are connected here, but since I just have 1, 1, 1, 2, 1, 3, I could change the properties of this a little bit, change my bin settings. Like right now it's just going by half, or like this 0.05. Let's say I put these together in 0.2 or something. Let's try that. There you go. This is more what we're used to seeing with histograms. There you go. Okay, so that's a histogram. And you also have, I think most people are familiar with histograms. We also have box and whisker plots. You can see outliers here. You can also see that this has been broken into quartiles. You can see I have 15 data points in my list. So when you look at this, you're going to say, oh, there's 25% of that 15, whatever that is going to be in this group, and then 25% in here, 25%, 25%. That's why they call them quartiles in the first place. So we have the first quartile, the median, third quartile, and maximum minimums. Okay, and you can see that there's an outlier here, which we'll talk about later in the year as we get going. Okay, each graph that you see, whether it's a histogram or a box plot or whatever it is, has its pluses and minuses. And these are something you need to know. You need to be able to say, this is an advantage by using this type of display. For a box plot, it's nice because you can see the percentages. You can see where the groups are, the lower group, the middle groups, and the upper group. You can really distinctly see those. A disadvantage to a box plot is you can't see the individual numbers. I don't know if I have 5 numbers over here and 1 number over here, or if I have 5 numbers on the left and 1 number on the right. I don't know where these numbers are exactly. I don't know the distribution of it very well. I just know it kind of in chunks, right? I know the distribution in chunks. Versus a histogram, or let's go back to a dot plot actually. A dot plot, I can see every single data point. And I can count them up too, right? I can see, oh, there are 15, 1, 2, 3, 4, 5, 6, 7, 8. And I could probably count those up and get how many data points there are. On a box and whisker plot, you have no idea how many data points there are. Are there 10 or are there 1,000? You would have no idea by just looking at the box and whisker plot. So everything has its advantages and disadvantages. It's your job to know what those are. Okay, so what I showed you are 3 different ways to display quantitative data. Things like speed and height and weight, and things that are numerical. How do we display categorical? Well, a lot of times categorical is like, what's your eye color, or are you male or female, or whatever, and whatever, something that is not numerical. How many chairs and desks and pencils, or whatever, things like counts of things, right? So quantitative and categorical. I'm going to come back to this in a second. So how do we display categorical? Well, instead of a histogram, a lot of times we use a bar chart. You can see here we have the classes of the Titanic, first class through third class, and then crew members. So this is categorical. It's just counts of people in those different classes on the Titanic. Now, a bar chart is one way. We also have a relative frequency chart. This is comes up a lot. and something you definitely need to know, relative frequency just means percentage. So we take those counts and we change them into percentage. It's just a nice way to compare things. You could have a pie chart. We all know that pie charts work on percentage too. You can see the counts are listed here, right? We have the counts, but to actually make the pie chart, you need to figure out what those percentages are to come up with the right size of a slice, right? Out of 360 degrees. You can put those, oh, here we go. You can put those together in what's called a segmented bar chart, which is really nice. Again, the pie chart has percentage, and then you can put those into a percentage on a bar chart. And this is really nice to see when you group it like this, because it's really easy to compare the groups. I mean, I can compare this green pie slice to this green pie slice. That's fine. But I could also do it over here, this green section to that green section, and compare them, right? First class, second class, third class. In this case, we're talking about alive and dead, who end up, alive depending on their class, and who ended up dying on the Titanic depending on their class. As you can see, the higher the class goes, the more people were able to stay alive, right? The lower the class, more people died, percentage-wise, especially. Okay, so that's some different ways you can look at categorical data. Let's go to the contingency table, I guess. Actually, let me go back here. Sorry, I'm going to jump back here. Okay, this is what's called poser numbers. And, I said, quantitative is numerical and categorical is just things like eye color and stuff like that. But sometimes people put a number on something that's categorical, and they just do that to make it easier for them. Maybe they don't want to write the words out, so they just put a number on it. You got to be careful with that, because now as soon as you've like associated that with a number, all of a sudden people start thinking they can do things like take the mean and the median of those, which wouldn't make any sense. I mean, think about it. If uh, I took like 23 ones and 19 twos and 14 threes and 4 fours, and I added all those up, and I got and then I took, divided by how many I had, and I did an average. I mean, some people, you could do that with the numbers, but it wouldn't mean anything. It would just be stupid, because you'd be doing like an average race, which wouldn't make any sense at all. So we call those poser numbers. They kind of fake people out, because it looks like it's quantitative, but it's really just categorical. It's just a different way of writing a category. So be careful of stuff like that. I'm going to skip that. Not important. Contingency table. This is probably the last thing that we need to talk about as far as displaying data. Very, very important. We do this a lot. When you go and collect data in the world, one of the first things you're probably going to do is just throw it into a table, right? What are my counts for all the things that I was asking people about, right? So this is still that Titanic data, but you can see they have it as a numerical category up here where it's categorical, and it's just a count of data. And then they change that into percentages down here, right, with the percentages. And then those percentages then were changed into pie charts and segmented bar charts, right? So we're going to work with this. Okay, now when we work with contingency tables, a lot of times we're asking ourselves, is there independence or dependence? Independence is a big thing we talk about in this class, and it's kind of synonymous with association. So you're going to see the word association a lot. Okay, so what is association or independence between things? If something's independent, that means they have no association, right? If they're not independent, that means there is an association. So what we're looking at here is flavor of ice cream, and then the category of children, teens, and adults. Basically, all we're asking is, are the percentages of children and the percentages of teens and adults, are they the same for the different flavors of ice cream? Like, does everybody like chocolate more than they like vanilla? I can see here that we got 40 chocolate for children, but only 22 vanilla. So when I start looking at the data, I can start to say, well, probably not. But sometimes it's hard to tell by the numbers, because maybe this is 40 and 22, and this is like, I don't know, 30 and 28 or 30 and 20 or something. And you're just not sure. So you have to really know whether there's an association or not, whether it's independent, you need to look at the percentages. So what you do is you just change all these into percentages, and then see if those percentages are the same or not. And it's pretty, in the beginning, it's really simple. one of the last things, it's funny that we start with this because one of the last things you're going to learn this year is something called the chi-squared test. And the chi-squared test is going to like be able to really statistically tell you whether something is independent or not. Right now, we're just looking at percentages, and we're just going to say, are these percentages the same or not the same? Okay, now I did the work on this uh, online. So I went online, and they have this kind of setup. You can write in your categories over here, chocolate, vanilla, neither, and you can also put in the numbers for the different pieces. So you can see right here, I put in the children, teen, and adult. Now I put it in as percentages. So I went ahead and I changed all of these numbers into percentages first. Okay, and then after I did that, I put it in the website, and then the website was able to spit out the segmented bar chart for me, which is exactly what I wanted, and I have it as a relative segmented bar chart, relative frequency segmented bar chart. Okay, so you can see it goes up to 100 because it's percentage. And I can see really easily here that those percentages are not the same. I mean, I probably could have just looked at the numbers, but this visual, which is kind of the whole point of these two chapters, is what's a good visual to display your data. And you can see this is a really nice way of doing it. I can see these yellow sections are not the same size. These black sections are closer, but really not the same size. And the blue ones are not either. All right, so if you have independence, then these sections would be exactly the same size. All the yellows, all the blacks, and all the blue sections would be the same size. So when I look at this, I'm going to say, oh, there is no association between the flavor of ice cream and the preference from the different age categories, children, teens, and adults. Right? Put it into context, and you would say, "Wow, there's no association because the percentages are different." Or sorry, I take that back. There is an association, right? So they are not independent. It depends. I'm sorry, I messed that up. So they are not independent. There is an association. So not independent. There is an association. The reason let me kind of word it a little differently. So the flavor of ice cream that people like depends on what age category they're in, whether they're a child, a teen, or an adult. If you're a child, your preference for ice cream flavor is different than a teen or an adult. So the ice cream flavor choice depends on what you are. So it's dependent, it's not independent, which means there is an association. Sorry if I messed you up in the beginning there. Okay. All right, let's move on. One more thing, I think, yeah, last thing is called Simpson's paradox. Simpson's paradox is just something you need to watch out for. Here's one situation. Things, like I said earlier, they don't always seem like they should, or people use stats to kind of support their agenda. This is one way it kind of pops up sometimes. This is a math problem. You and your friend do some math problems on Saturday. On Saturday, you do 8 problems and get 7 of them right. Your friend gets 2 out of 2 right. So it looks like your friend has a higher percentage, 100% and you only had 87% correct. Now you got to keep in mind it's the numbers that are causing what we're going to see here. He only did 2, he or she, and you did 8. So that's where the problem comes in. On Sunday, you did 2 problems and you got only one of those right. And so you get 50%. Well, your friend did 8 and they get 5 of them right and they have 62%. So on Saturday, they got 100% right. You only got 87. On Sunday, they got 62% right and you only got 50. So when you look at this, you're like, well, your friend beat you on both days. So obviously they're better at math than you. They do better on their math problems. But if you look at the totals, you can see on the first day you did 8, and the second day you did 2. That gives you a total of 10, and for them they did 10 as well total. If you look at the total numbers, you got 8 out of 10 right, and they only got 7 out of 10 right, which means you were actually better on the math problems than they were. So this is what's called Simpson's paradox, because it looks like individually that one thing is better than the other, but when you look at it as a total, it's the reverse view. So that's confusing, and it's a paradox, and that's why it's called Simpson's paradox. Is it wrong? Is there something that's gone wrong or something? No, that's just statistics. It's you got to be able to really analyze what you have in front of you in the proper way. And why is this happening? Well, like I said, it's just the numbers. Here the percentage that we calculated was only coming from 2 versus 8, and here it was the reverse, 2 and 8. So it was kind of the percentages got a little skewed, not skewed, but they look skewed, just because of the number of problems each of you did each day. If you would have done the same number of problems every day, then you wouldn't have had this paradox then. And that's something simple, not a big, I mean, that's not an important situation, but it does show up in important situations. There's some famous stuff about, I forget what school it was. Gosh, I can't remember. Some big school or whatever had problems with their enrollment in the different categories of their businesses, and whether it was engineering or business majors and stuff like that. And so they had big problems with that, and they were trying to analyze it, and their Simpson's paradox came up. Also, here you can see this is about like the death penalty, for violent offenders and murderers and stuff. And at first they separated into Caucasian and African American for the defendant, and then they looked at how many were put to death and how many were not put to death, for their sentence. And when you look at it this way, you're like, hey, wait a minute, everybody's complaining that, oh, African Americans get put to death more than Caucasians do. That's what people would say. But when you looked at the numbers, you would say, well, out of all these people, only 53, well, 53 out of the total were put to death, which is 11%. And if you look at the 15 out of the total of the African Americans, it's only 7.9%. So some people would use this data and say, hey, you got no leg to stand on because it looks like the Caucasians are getting sentenced to death at a higher percentage rate than the African Americans are. But if you separate it out by who the victim really was the victim themselves Caucasian, or was the victim an African American? Then there's a different story going on. So you can start to see that when the victim was a Caucasian, then the percentage of African Americans who were sentenced to death is way higher than the Caucasian. And same thing for the African American. So like when you look at the Caucasians, if the victim was an African American, then like nobody was sentenced to death. And this is a very specific situation of in the past, right? This isn't current data. This is really old by now. But you can see where the Simpson's paradox comes in, and how data can be used to kind of support your cause sometimes. And so it's important for us to really dig in and find what the real truth is. Okay, I think that covers chapter 1 and 2. There's other little things you should be picking up from the textbook. Again, make sure you read the textbook. You can't do well at this course unless you read and study the textbook. When you come to class, we're going to be working problems, and you need to be ready before you get there. All right, let us know if you need anything. Thank you very much.